Alright, let's begin. So today I'm going to do a paper called Perceptually Guided Speech Enhancement using Deep Neural Networks. And this is a paper by Zhao, Zhu, Gary, and Zhang, a group from Ohio State University and Starkey Hearing Technologies. Okay, so I'm not the author of this paper. I'm just presenting their work. But hopefully you will find this presentation useful if you're learning about speech enhancement. Anyways, so I looked up the company that did this, and the company that's doing this research is called Starkey Hearing Technologies. That's the group that's affiliated with this paper, and they make these hearing aids. So actually a lot of people, a few million people in the country have some kind of hearing impairment, and if you have some hearing impairment, then often you will use these devices to help you hear better. So depending on what kind of hearing impairment you have, you might wear one of these on your ear like an earbud, or you might wear them inside your ear. And not only do they amplify the voice for you, they are also might use some AI, some machine learning algorithms to make it more clear so you can understand it better. So this is why speech enhancement can be useful if you for people that have hearing impairments, to enhance the speech so you can hear it better. So let's look at the task that this paper does. It's a speech enhancement. So basically what we're trying to do is turn some noisy speech into clean speech. You're given some speech that's noisy, that has some noise, and you're trying to turn it into a form that's easier to understand. And we use machine learning to do this. So before you can delve into any models, you have to decide, okay, how do you want to evaluate the system? How would you evaluate if you got two models that do speech enhancement, which one is doing it better? And it's not quite obvious how you would do this. If you do have some kind of ground truth, like you know what it's supposed to sound like, you can try using something like mean squared error between the output and the ground truth. Like you would run the spectrogram over both of them and decide on mean squared error between them. But it turns out that this is not really a good metric for intelligibility, in the sense that if you got high mean squared error, it's not necessarily bad and unintelligible. So other people have developed metrics that are more closely correlated with speech intelligibility. So we're going to go over that later. Now, how would you do this? So now we're going to look at some work in the past that people have invented to measure the intelligibility of speech. So you will do this to compare models and evaluate how well your model is doing at turning noisy speech into cleaner speech. Now, I guess the first and most obvious way you might do it is to use subjective testing. So then you would give your output of your system to a bunch of people and ask them to rate on a scale, say from 1 to 5, on how intelligible the speech is. And depending on what group you use, you might use normal hearing people, or you can use people that have hearing impairments. And depending on what group you use, you might get different results on which model is better and which model is worse. So this is a way to do it. And the problem with this is it's really time consuming and expensive. Like every time you run the model, you have to get a bunch of people to rate it and report back on the results, and this is just really time consuming and expensive, so it's rarely ever done in practice. So in practice, you will actually evaluate it automatically. You would use some kind of automatic evaluation metric to determine how well your model is doing. And there's two ways of doing this. There's you can either use an intrusive metric and a non-intrusive metric. So the difference between this is an intrusive metric requires you to have some kind of reference signal to compare it against. So your model has some kind of output, and then you would compare it against some kind of reference signal, so a clean version of it, you will need this for intrusive metric. And here's there's a list of metrics that people have come up with to do this. And in contrast, our non-intrusive metric would be a metric that does not require reference signal, so only requires the a sample of speech, and that's enough for it to tell you whether or how intelligible it is. And a non-intrusive metric is slightly more flexible, but actually in practice it's not that big of a problem to use an intrusive metric, because you would normally generate your data by taking a clean sample and like superimposing a noisy sample. So then this generates your noisy speech from the clean speech. So then you will train your model to go from noisy speech to clean speech, where the noisy speech is kind of synthesized as a clean speech plus some noise sample, right? So then you would have the clean speech as well when you're doing evaluation as well. So it's perfectly fine to use an intrusive metric, because you would have the reference signal to compare it against. And now we're going to look at some examples of non-intrusive and intrusive metrics. So one example of a non-intrusive metric is ModA, Modulation Spectrum Area. And this is a non-intrusive metric, so it does not require any kind of reference signal for it to work. And how it works is it measures the amount of reverberation in a signal. So reverberation is when you're in some kind of room and then you say like hello, and then it comes kind of back to you it's not quite the same as echo. Echo is when it comes back to you like clearly. Reverberation is like it comes back to you kind of like hello. Anyways, it's hard to describe it, but there are mathematical ways for you to for algorithm to figure out how much reverberation is in a signal, and this measure this just measures how much reverb is in the signal and uses that as a metric for how intelligible it is. And it turns out for normal hearing people don't really have much problem with this. You can have very high levels of reverb and it's still fairly intelligible, but people with hearing impairments have a lot more difficulty with this, and having some level of reverb would make it very difficult for them to understand, and that's why they decided to use this kind of metric. But this is kind of a side. It's not actually used in this paper, just FYI. And now what's used in this paper is STOI, short time in objective intelligibility. So this is an intrusive metric, so it does require a clean reference speech sample. Right? Okay, so over here, you have the clean speech and the degraded speech. That's your input to this algorithm. And first, what you do is you compute a discrete Fourier transform, so a bunch of filter banks to get this spectrogram-like structure. Right? So you use actually 24 of these filter banks, where each filter extracts a 1/3 octave band, and now you have a spectrogram for the clean speech and a spectrogram for the degraded speech. And now you compute the correlation coefficient between the spectrograms at each band. Right? So let's say for the top band, you would compute the correlation between the top band of the clean speech and top band for the degraded speech, and this gives you a correlation coefficient, right? And then you do this once for each of these bands. It's 24 bands, so you do this 24 times. You calculate the correlation coefficient between each between this band at each time step for the clean speech and degraded speech. So you got a vector of intensities for the clean speech signal, and you got a vector of intensities for the degraded speech signal. You do a correlation coefficient, and now you average them. You average them across all of the 24 bands, and this gives you the STOI metric. And additional thing to note is they do a sort of normalization clipping here for the degraded speech, and it turns out that that this is required because like after a certain amount of degradation, your signal is degraded enough that it doesn't really matter if it's degraded anymore. It's already so unintelligible that you might as well count it 0, and then you shouldn't penalize it further for being more intelligible after a certain point. Okay, so why does it make sense to do the correlation coefficient? Well, let's think about an example. Like let's say you have a degraded speech signal that's kind of like a clean speech, but just like a little bit quieter, let's say quieter by 20%. Then by measuring the correlation coefficient, you would still be correlated. Like if this signal is the same as the original signal but just 20% more quiet, then the correlation coefficient is gonna be perfectly correlated, right? But then if you actually add noise, if you add like uniform independent noise to the signal, then this would decrease the correlation coefficient, right? But in contrast to something like MSE, if you're using MSE, then you would increase the MSE in both cases by a similar amount, whether you add a constant multiplicative factor or if you add noise. But with correlation coefficient, it more closely measures how much noise you're adding to the signal. Okay, so this is kind of just the previous slides, but in equations instead of a picture. So the first equation here is measuring the correlation between two signals. So this is so J is the band, like the frequency band, and xj and yj and x and y are the vectors that you're at this band, and dmj would be your correlation between one x band and one y band. So now your dm would be the STOI metric. So the average of dmj's across all 24 frequency bands. This is the definition of the STOI metric. And now the loss function that they use for the algorithm is a linear combination of the STOI metric plus MSE. So they decided that STOI metric is not quite enough. They want to combine it with MSE here. And they have a hyperparameter lambda that decides how much to weigh the STOI part of this loss function with the MSE part of the loss function. So why do they use MSE here? Well, it turns out that STOI isn't enough because it only considers frequencies below a certain threshold. So you can imagine that it only covers frequencies below a certain point, and then anything above this certain frequency threshold doesn't affect the STOI metric at all. So then you could have a signal that's really degraded above this certain frequency, and then it wouldn't be captured by this loss. So then you have the MSE here that does capture some of it. So they combine the STOI loss with the MSE loss to get your final loss function to train the model. And another interesting thing, before I show you the full model, another thing is the idea of mask prediction. So ultimately, you have to find a way for it to turn for a neural network to turn a noisy speech sample into a clean one. And probably the most obvious way to do it would be just give it the noisy speech as input, and then and then have it output the clean speech as output. But it turns out the slightly better way to do it would be to do mask prediction. So instead of outputting the clean speech signal, it would instead just output a mask, kind of which frequencies are considered clean, the signal, and which frequencies are considered noise. So here you would have some kind of spectrogram, and then your neural network would be given some parts of it as input, and then it will output this vector, this kind of mask, and then depending on the output, then some parts of it would be weighted more and some parts of it would be weighted less. So here, for example, you have the ones at the top, which mean that this would be counted as the signal, and then the noisy part, let's say that this part is noise, then it would weigh it really low, so then the output would filter this out, right? So this is kind of like a high pass filter where you only get high frequencies, and then the low frequencies get filtered out as noise. So this is a little bit easier for the neural network to work with than trying to go directly from the input to the output. So it will predict a mask instead, and then have the mask be multiplied with the input to get the output. Alright, so now let's look at the entire model. Okay, so first you have the yellow part, which is the noisy speech, and then you have the green, which is the clean speech. And now the blue is predicting the racial mask. So you have a neural network that takes in features to predict the racial mask, and then this mask is multiplied with the noisy speech to get a clean speech, which is then compared with the actual ground truth clean speech to go through the loss function. So first the STOI loss function, and then the MSE loss function, and then all of that is combined together to get the combined loss function, which is and all of this is end-to-end differentiable, so you can do backpropagation and learn all the weights of these neural networks. So these guys are doing the heavy lifting, and the features that they take as input are 5-frame context windows. So this does it kind of one frame at a time, right? So for each frame, it gets 5 frames of context around it as features, and then it predicts this racial mask, and then this racial mask like this is multiplied with this frame at this point, and then all of this is concatenated together and then turned back into a signal, and then yeah, so in the training phase, you would get the loss function by comparing it with the ground truth clean speech, and obviously in the evaluation phase you wouldn't have the ground truth, so then you would only have the yellow and blue parts, and then you would just output the clean speech signal by doing this. Okay, now let's look at some of the experiments. So the dataset that they use is first the IEEE corpus of clean speech of recorded sentences. So they have a bunch of sentences spoken by one person in a clean, fairly noiseless environment, and then they have ways of adding speech-shaped noise, and they have this NoiseX database, which contains a bunch of noise from different places, like speech babble, and then noise from a factory floor, and then noise from a destroy engine room. So all kinds of different noises, and then they synthesize the noisy speech by adding this noise to the clean speech, and then they make sure to split it so that they use a different part of the noise set to generate the training and the evaluation, so that the noise that you use for evaluation is not seen in the training data. And now they have a few ways of doing it. So you have the unprocessed noisy speech signal kind of as a baseline. You have SA, which is a kind of unrelated paper, and now you have you have 4 of these neural network approaches. So first you have 2 ways of doing the loss function, and you have 2 ways of doing either mapping or masking. So mapping, which is the first one, and the third one is by making the neural network go from the input signal to the output signal directly, whereas masking is making it predict the ratio mask and then multiplying that to get the output. And then here you have both the normal typical MSE loss and then the proposed loss, which is a combination of MSE and the STOI loss. Right, so you have both the mapping and masking multiplied by the MSE loss and proposed loss. So this gives you 4 different combinations. And here's the results. So they found that the proposed approach, which does masking and the proposed loss, works the best here. So we're looking at this table here. This table is when you're measuring by STOI metric. If you measure by STOI metric, then it beats the other baselines like SA and masking by around 2% across conditions. So here you have 81.99. Here you have like 80.01. So it's around 1 to 2% improvement for the STOI metric. But then if you look at the PESC metric and the STOI metric, like these are different ways of measuring speech intelligibility, then the results are not so clear. Then it actually doesn't really outperform the baselines in most cases. So this is a little bit worrying because it only beats the baselines by a little bit, and only does it when you measure the STOI metric. So the problem is it's trained to optimize the STOI metric. By definition, that's what it's trained to optimize. And yeah, sure, of course you would expect it to do well on the STOI metric because that's what you trained it to do. But then does it generalize to other metrics? Well, it doesn't seem like it does. So it's not so clear whether this is more of hacking the reward metric or actual legitimate performance increase here. Okay, so let's conclude this. So in summary, this paper proposed a new method of doing speech enhancement by optimizing for STOI, which is a perceptually guided speech intelligibility metric, and it does experiments, and it found that it does improve upon some baselines compared to if you also evaluate doing this STOI metric. Okay, now some of the caveats, as I said, is how much of the improvement is legitimate, and also the question of metric is why there's so many different metrics for this problem. There's so there's been studies on which metrics do correlate best with human judgments of intelligibility, but you also have all these different metrics that you're optimizing. And okay, now you do have the STOI, which is a pretty good one, but even then they still over here they still have to modify the STOI metric by adding it by augmenting it with MSE metric. So STOI somehow was not quite what they wanted here. They had to change it a little bit and add part of the MSE metric in the loss function. So it's all these different metrics, and I'm wondering if STOI is actually the right one for evaluation, if it's not the right one for training. So yeah, pretty interesting research, but some caveats here. Yeah, hopefully you learned a little bit about using deep learning for speech enhancement. Yeah. Thanks.